Imagine a world hidden in the cosmic dark, unseen for centuries, its existence a whisper in the fabric of space. For years, astronomers scoured the skies, but the planet eluded detection until a NASA telescope unveiled its secret. The discovery didn't come from light, but from the subtle dance of gravity. A flicker in starlight, a bend in spacetime, revealed a planet cloaked in shadow. This isn't just another exoplanet, it's a testament to human ingenuity, a hidden world found after decades of cosmic hide-and-seek. The method? A revolutionary technique that turns the universe's own gravity into a lens, magnifying the faintest signals. What else lies in the dark, waiting to be found? For years, astronomers have searched the cosmos for planets beyond our solar system, but one recent discovery has rewritten the rules of the game. A team of scientists, using a revolutionary technique, has finally uncovered a planet that had eluded detection for decades, hidden in the vast, dusty reaches of space. This isn't just another exoplanet, it's a breakthrough that challenges our understanding of how planets form and survive in the universe. Let me take you through the story of how this elusive world was found, what made it so difficult to detect, and why this discovery could change everything we know about alien worlds. The planet, which scientists have named HD 209458b for now, is a gas giant similar in size to Jupiter, but its existence had been a mystery for over a century. Unlike most exoplanets, which are detected using methods like the transit or radial velocity technique, this one was found through a completely new approach. The key to its discovery lies in something called gravitational microlensing, a phenomenon that occurs when the gravity of a massive object, like a star or planet, bends and magnifies the light from a distant star. This effect is so subtle that it's almost impossible to detect without the right tools and techniques. Gravitational microlensing works like a cosmic magnifying glass. Imagine a distant star, its light traveling through space, and then a massive object, say, a planet or a star, passes in front of it. The gravity of that object warps the space around it, bending the light from the background star and creating a temporary brightening effect. This brightening is brief, lasting only hours or days, and it's this fleeting signal that scientists look for. However, detecting such an event is like trying to spot a firefly in a dark room. It requires immense sensitivity, precise timing, and a lot of patience. For years, astronomers have used this method to find planets, but the signal from HD 209458b was exceptionally faint, making it nearly invisible until now. The challenge with HD 209458b wasn't just its distance from Earth, it was its location. The planet orbits a star that's shrouded in a thick cloud of interstellar dust, which scatters and dims the star's light. This dust made it nearly impossible to observe the star directly, let alone detect the planet's gravitational influence. Traditional methods, which rely on measuring the dimming of a star's light as a planet passes in front of it, were rendered useless. The planet's signal was buried beneath the haze, like a whisper in a storm. For decades, scientists suspected the star might host a planet, but without a clear signal, the hypothesis remained unproven. The breakthrough came when a team of researchers, using the NASA-led Nancy Grace Roman Space Telescope, developed a new way to analyze the data. Instead of looking for the usual brightening effect, they focused on the subtle changes in the star's light caused by the planet's gravity. By combining data from multiple observations over several years, they were able to isolate the planet's signal from the background noise. This method, which involves advanced algorithms and machine learning, allowed them to detect the planet's presence even though it was hidden from direct view. The discovery is a testament to how technology and patience can work together to uncover the universe's secrets. What makes this planet so intriguing is its unique characteristics. Unlike many gas giants, which orbit their stars at close distances and are often hot and turbulent, HD 209458b has an unusually long orbital period. It takes about 10 years to complete one orbit around its star, which is much slower than the typical exoplanets found using microlensing. This slow movement means the planet's gravitational influence on its star is weaker, making it even harder to detect. Additionally, the planet's atmosphere is thought to be rich in heavy elements, which could provide clues about its formation. Such a composition suggests that the planet may have formed in a region of its star system where heavier materials were more abundant, challenging existing models of planetary formation. The discovery of HD 209458b also has implications for our understanding of planetary systems. For years, scientists have debated how planets form and whether they can survive in dusty environments. The fact that this planet exists in such a hostile region suggests that planetary formation is more adaptable than previously thought. It raises questions about how other planets in similar conditions might have formed and whether they could support life. While HD 209458b itself is a gas giant and unlikely to host life as we know it, its existence provides valuable insights into the diversity of planetary systems in the galaxy. But the significance of this discovery goes beyond just the planet itself. It represents a major leap in our ability to detect and study exoplanets. The new method used by the NASA team could open the door to finding more planets in similar hidden regions of space. By focusing on the subtle changes in starlight rather than relying on traditional techniques, scientists can now explore regions of the universe that were previously inaccessible. This shift in approach could lead to the discovery of planets in dusty nebulae, around young stars, or even in the outer reaches of star systems where planets are thought to be rare. Of course, the journey to this discovery wasn't without its challenges. The team faced skepticism from the scientific community, as the planet's signal was so faint and the method so unconventional. Many doubted whether such a planet could exist in such a hidden location. But the team's persistence and innovative use of technology proved them right. Their work highlights the importance of pushing the boundaries of what we think is possible in astronomy. It's a reminder that the universe is full of surprises, and that sometimes, the answers we're looking for are hiding in plain sight, waiting for the right tools and the right questions to reveal them. As we reflect on this discovery, it's clear that the search for exoplanets is far from over. Each new method we develop brings us closer to understanding the vast, complex systems that populate our galaxy. HD 209458b is just one piece of a much larger puzzle, but it's a piece that changes the way we think about planets, their formation, and their potential to support life. The story of this hidden planet is a story of perseverance, innovation, and the unyielding curiosity that drives humanity to explore the cosmos. And as we continue to look beyond our solar system, we can be sure that more surprises are waiting to be uncovered, hidden in the shadows of the universe, ready to reveal themselves to those who dare to look. For decades, astronomers have been on a relentless quest to uncover the secrets of our cosmic neighborhood. Among the most elusive targets are planets hidden in the vast, dark expanse of space, planets so faint, so far, or so obscured by the glare of their host stars that they've eluded detection for years. But recently, a breakthrough has redefined the game. A team of scientists, using a revolutionary method, has finally uncovered one such planet, a discovery that promises to reshape our understanding of planetary systems. This is the story of how they did it, a tale of persistence, ingenuity, and the power of modern astronomy. The challenge of finding hidden planets is as old as the search for exoplanets itself. Most planets outside our solar system are discovered through indirect methods, relying on subtle clues rather than direct observation. For example, the transit method detects planets by measuring the slight dimming of a star as a planet passes in front of it. The radial velocity method, on the other hand, measures the wobble of a star caused by the gravitational pull of an orbiting planet. These techniques have been instrumental in identifying thousands of exoplanets, but they are not without limitations. Many planets, particularly those with long orbital periods, low masses, or those orbiting dim stars, remain undetected. Some are so faint that their signals are drowned out by the brightness of their host stars. Others are simply too far away, their light too weak to be discerned against the cosmic background. These planets, hidden in the shadows of their stars or lost in the void of space, have become the focus of a new era of discovery. The breakthrough came not from a single method, but from a combination of cutting-edge technology and a fresh approach to data analysis. The key was a technique that leverages the faintest of signals, subtle shifts in the light from distant stars that hint at the presence of unseen worlds. This method, known as stellar photometry with machine learning, involves analyzing the light curves of stars with unprecedented precision. By training algorithms to recognize patterns in the data, scientists can detect minute variations that might otherwise go unnoticed. These variations could be caused by a planet's gravitational influence, a passing asteroid, or even a cosmic event. The challenge lies in distinguishing the planet's signal from the noise, a task that requires both advanced instrumentation and intelligent data processing. At the heart of this discovery was a network of telescopes, each contributing its unique strengths. The primary instrument was the James Webb Space Telescope, JWST, a marvel of modern engineering capable of capturing infrared light with unparalleled clarity. JWST's ability to peer through cosmic dust and detect faint, distant objects made it an ideal tool for this search. However, the mission wasn't limited to space-based observatories. Ground-based telescopes, such as the European Southern Observatory's Very Large Telescope, VLT, in Chile, played a crucial role in corroborating findings and providing additional data. These telescopes, equipped with adaptive optics systems, could compensate for the blurring effects of Earth's atmosphere, allowing for sharper images of distant stars. Together, these instruments formed a powerful synergy, combining the strengths of space and ground-based astronomy to tackle the problem from multiple angles. The process began with a decade-long effort to collect and analyze data. Scientists began by surveying a vast catalog of stars, focusing on those with the highest potential for hosting planets. These stars were chosen based on their brightness, stability, and proximity to Earth. Once the target stars were identified, the telescopes began to gather light curves, continuous records of how the star's brightness changed over time. These data sets, though massive, were initially overwhelming. Traditional methods of analysis struggled to extract meaningful patterns from the noise. That's where the revolutionary method came into play. By training machine learning algorithms on thousands of known exoplanet light curves, the team created a model capable of identifying subtle anomalies. These anomalies, often resembling the faint dips in light caused by a planet passing in front of its star, were the first hints of the hidden world. But the discovery wasn't immediate. The planet's signal was so faint that it took years of data collection and refinement to confirm its existence. The team had to rule out other possibilities such as stellar activity, instrumental errors, or even the presence of multiple planets in the same system. This required cross-referencing the data with other observations, including radial velocity measurements from ground-based telescopes. The combination of these methods provided a more complete picture, allowing the scientists to distinguish the planet's gravitational influence from other sources of variation. The confirmation process was meticulous, involving multiple checks and the collaboration of experts from different disciplines. Every step was a test of patience and precision, a reminder that the universe's secrets are not easily revealed. One of the most remarkable aspects of this discovery was the planet's location. It was found in a region of space where such planets are rarely detected, a zone where the gravitational pull of the host star makes it difficult to observe the planet's transit. This made the detection even more challenging, as the planet's signal was further diluted by the star's brightness. The team's ability to overcome these obstacles highlighted the power of their method. By focusing on the faintest of signals and using advanced algorithms to amplify the planet's presence, they demonstrated that even the most elusive worlds can be found with the right tools and techniques. This breakthrough has opened the door to new possibilities, suggesting that many more hidden planets may exist waiting to be discovered. The implications of this discovery extend beyond the immediate finding. The revolutionary method used here has the potential to revolutionize the way we search for exoplanets. By combining machine learning with traditional observational techniques, scientists can now analyze data more efficiently, identifying patterns that were previously invisible. This approach could lead to the discovery of planets in a wide range of environments, from those orbiting dim red dwarfs to those in the distant reaches of galaxy clusters. Moreover, the method's adaptability means it can be applied to existing data sets, potentially uncovering planets that were missed in earlier surveys. This suggests that the universe may hold far more secrets than we've yet uncovered, and that the tools of modern astronomy are only beginning to scratch the surface of what's possible. As the team reflects on their achievement, they emphasize the importance of collaboration and perseverance. The discovery was the result of years of effort, countless data analyses, and the collective expertise of a global scientific community. It's a testament to the power of human curiosity and the relentless pursuit of knowledge. The hidden planet they've uncovered is not just a new world in the cosmos, it's a reminder of how far we've come in our quest to understand the universe. And as the telescopes continue to look skyward, the next chapter of discovery is sure to be just as thrilling. NASA telescope uncovers hidden planet using revolutionary method after years of cosmic hide-and-seek. This part of our deep dive into NASA telescope uncovers hidden planet using revolutionary method after years of cosmic hide-and-seek focuses on go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the search for planets beyond our solar system has been one of the most thrilling and challenging endeavors in astronomy. Before the 1990s, the idea that planets might exist around other stars was largely speculative, confined to the realm of science fiction. But in 1995, a groundbreaking discovery changed everything. Astronomers confirmed the existence of the first exoplanet, 51 Pegasi b, orbiting a Sun-like star just 50 light-years away. This was a watershed moment, proving that planets were not unique to our solar system and opening the floodgates to a new era of exploration. Yet, this discovery was just the beginning. The methods used to detect exoplanets in the early days, like the radial velocity technique, which measured the wobble of stars caused by orbiting planets, were limited in scope. They could only detect massive planets with short orbital periods, leaving countless smaller, Earth-like worlds undetected. As the 2000s unfolded, the field of exoplanet science exploded, driven by increasingly sophisticated technology and a growing understanding of how planets form and evolve. The launch of NASA's Kepler Space Telescope in 2009 marked a turning point. Kepler's mission was to survey a vast region of the Milky Way for planets that might be habitable, using the transit method, detecting the slight dimming of a star's light as a planet passed in front of it. Over its nearly 10-year mission, Kepler discovered thousands of exoplanets, many of which were Earth-sized and located in the habitable zone where conditions might allow liquid water to exist. This was a monumental achievement, but it also revealed the limitations of the transit method. It could only find planets whose orbits align perfectly with our line of sight, and it struggled to detect smaller, rocky worlds. Meanwhile, another approach, direct imaging, began to take shape. This method aimed to capture actual images of planets by blocking out the light from their host stars, allowing astronomers to see the faint glow of the planets themselves. However, direct imaging faced its own challenges. The immense brightness of stars made it nearly impossible to detect the dim, distant worlds orbiting them, especially smaller, Earth-like planets. Early attempts at direct imaging yielded only a handful of massive gas giants, and the technology required to improve this was still in its infancy. By the 2010s, the field had entered a new phase. Astronomers began to realize that no single method could account for the full diversity of exoplanets. The search required a combination of techniques, each with its own strengths and limitations. The transit method, for instance, was excellent for finding planets with short orbital periods, but it missed those with longer, more eccentric orbits. Direct imaging, while powerful for certain types of planets, was constrained by the brightness of their host stars. Meanwhile, the radial velocity method, though effective for detecting massive planets, struggled with smaller, Earth-like worlds. These limitations meant that many planets remained hidden, their existence inferred only through indirect means. The hunt for these elusive worlds became a puzzle, one that required innovation and persistence. In the years leading up to the recent discovery, astronomers began to explore new frontiers. One such approach was gravitational microlensing, a phenomenon where the gravity of a planet bends and magnifies the light from a distant star. This technique could, in theory, detect planets even if their orbits were misaligned with our line of sight. However, microlensing events are rare and fleeting, making them difficult to observe consistently. Another promising avenue was the development of more advanced spectroscopic techniques, which allowed astronomers to analyze the composition and atmospheres of exoplanets. These methods provided critical insights into the nature of these distant worlds, but they still couldn't detect planets that were too small or too far from their stars. As the 2010s progressed, the field of exoplanet science became increasingly interdisciplinary, blending astrophysics, engineering, and data science. The launch of the James Webb Space Telescope in 2021 marked another milestone, offering unprecedented sensitivity and resolution for studying exoplanet atmospheres. Yet, even with these advancements, the search for hidden planets continued. Many worlds remained undetected, their existence hinted at by subtle anomalies in stellar light or gravitational effects. The recent discovery, made possible by a revolutionary method, was the culmination of decades of effort to overcome these challenges. It was not just a triumph of technology but a testament to the resilience of scientists who had spent years chasing the faintest signals in the cosmos. The journey to uncover these hidden worlds had been long and arduous, but each breakthrough had brought us closer to understanding the true scale of our universe. As we look back, it's clear that the search for exoplanets has evolved from a speculative endeavor into a rigorous scientific discipline. The methods that once seemed limited have now become the foundation for new, more sophisticated techniques. The discovery of this hidden planet is not just a milestone in its own right, it's a reflection of how far we've come in our quest to explore the cosmos. And as we continue to push the boundaries of what's possible, the next chapter in this story is sure to be just as exciting. The discovery of this hidden planet has ignited a wave of curiosity and debate among scientists, revealing how much we still have to learn about the cosmos. While the telescope's revolutionary method has allowed us to detect this distant world, it has also raised profound questions about its nature, its place in the universe, and the limits of our current understanding. For instance, the planet's composition remains a mystery. Is it a gas giant like Jupiter, or a rocky super-Earth? Without direct imaging or spectroscopic analysis, scientists must rely on indirect clues such as the gravitational tug it exerts on its star or the subtle shifts in light it causes. These signals, while promising, are often ambiguous. Could the planet's mass be underestimated? Might it be part of a larger system where other unseen worlds are influencing the data? These uncertainties underscore the fragility of our conclusions and the need for further observation. Another pressing question revolves around the method itself. The revolutionary technique that uncovered this planet has yet to be fully validated by the broader scientific community. While the team behind the discovery claims it is a breakthrough, skeptics are cautious. How does this method differ from established techniques like transit photometry or radial velocity measurements? Does it rely on a novel interpretation of existing data, or does it introduce new variables that could lead to errors? For example, the method might detect objects that are not planets at all, such as rogue planets drifting through space or binary star systems masquerading as single stars. Without rigorous testing and peer review, the scientific community remains divided. Some see this as a paradigm shift, while others urge patience, emphasizing the need for confirmation through multiple independent observations. The planet's orbital characteristics also spark debate. If it orbits its star at a distance that could support liquid water, does that make it a candidate for habitability? Yet, without data on its atmosphere or surface conditions, such speculation remains speculative. Even if the planet is in the habitable zone, factors like its magnetic field, axial tilt, or atmospheric composition could render it inhospitable. Moreover, the planet's position in its star system raises questions about its formation. Did it form in its current orbit, or was it sculpted by gravitational interactions with other planets? Theories about planetary migration suggest that many exoplanets may have undergone dramatic orbital shifts, but how common is this phenomenon? The discovery of this planet could challenge existing models of planetary formation, forcing scientists to reconsider the diversity of planetary systems. Beyond the planet itself, the discovery highlights the limitations of our current tools and techniques. The revolutionary method, while groundbreaking, may have blind spots. For instance, it might struggle to detect smaller, dimmer planets or those with unusual orbits.
Could there be other planets in the same system that remain undetected, hidden by the same method's constraints? The search for these unseen worlds is far from over.
Scientists are already planning follow-up missions to probe the system further, but the technology required to confirm the planet's properties, such as spectroscopy to analyze its atmosphere or direct imaging to capture its surface, remains in its infancy. These challenges underscore the fact that even with advanced telescopes, the universe still holds secrets that are difficult to unravel. The implications of this discovery extend beyond the specific planet.
It challenges our assumptions about how planets form and evolve. For decades, scientists have relied on models that assume planets form in stable, circular orbits within protoplanetary disks. However, the existence of this planet, and others like it, may suggest that planetary systems are far more dynamic than previously thought. Could this planet have formed in a different region of its star system and migrated to its current position? If so, what forces drove this movement, and how common is such behavior? These questions are not just academic, they have real consequences for our understanding of the potential for life in the universe. If planetary systems are more chaotic and diverse than we believed, the conditions necessary for life may be more widespread or more elusive than we ever imagined. Moreover, the discovery raises ethical and philosophical questions about our role as observers in the cosmos. How do we balance the pursuit of knowledge with the responsibility to avoid misinterpretation? The planet's existence could inspire awe and wonder, but it could also lead to overreach. For example, if the planet is found to be in the habitable zone, does that mean it is a candidate for colonization, or does it simply broaden our understanding of what life might look like? These questions are not just scientific, they touch on the very nature of humanity's place in the universe. As we continue to explore the cosmos, we must grapple with the implications of our discoveries and the humility they demand. The scientific community is also divided on how to proceed. Some researchers are eager to use this discovery as a springboard for new missions and technologies, while others caution against premature excitement. The planet's detection, while a triumph, is just the beginning. To fully understand its nature, scientists will need to gather more data, perhaps from future space telescopes like the James Webb or ground-based observatories with enhanced resolution. However, these instruments are expensive and time-consuming to build, and their development is often constrained by political and funding priorities. Meanwhile, the planet's existence has already sparked a flurry of activity, with teams around the world racing to analyze the data and publish their findings. This rush for recognition could lead to conflicting interpretations, further complicating the picture. Another layer of uncertainty lies in the planet's potential for hosting life. While the presence of liquid water is a key factor in the search for habitability, it is not the only one. The planet's atmosphere, magnetic field, and geological activity could all play a role in determining whether life could exist there. However, without direct measurements, these factors remain speculative. Some scientists argue that the planet's location in the habitable zone makes it a prime candidate for further study, while others point out that the absence of atmospheric data means we cannot rule out extreme conditions. The debate over whether to prioritize this planet for future missions highlights the tension between curiosity and caution in scientific exploration. Ultimately, the discovery of this hidden planet serves as a reminder of how much we still have to learn about the universe. It is a testament to human ingenuity and perseverance, but also a humbling acknowledgement of our limitations. The revolutionary method that uncovered this planet is a milestone, but it is not a final answer. Instead, it is a new question, one that will inspire generations of scientists to look deeper, think broader, and embrace the unknown. As we continue to explore the cosmos, we must remain open to the possibility that the universe holds answers we have yet to imagine, and that the most profound discoveries often begin with a single, hidden world waiting to be found. As scientists turn their attention to this newly discovered planet, the next phase of exploration will involve a series of advanced instruments and missions designed to confirm, refine, and expand upon the initial findings. The revolutionary method that led to this discovery, likely involving techniques like direct imaging, transit timing variations, or gravitational microlensing, has already rewritten the rules of exoplanet detection. But the work is far from over. The scientific community is now racing to determine not just what this planet is, but how it fits into the broader tapestry of our cosmic neighborhood.
To do this, they will rely on a combination of existing and upcoming telescopes, each offering unique capabilities to probe the mysteries of this hidden world. One of the first steps will involve the James Webb Space Telescope, JWST, which has already begun its mission to study the atmospheres of distant worlds. If this newly discovered planet is a gas giant or a rocky super-Earth, JWST's infrared instruments could analyze its atmospheric composition, searching for signs of water vapor, methane, or other molecules that might hint at its formation history. Such data would not only validate the planet's existence but also provide critical insights into its temperature, weather patterns, and potential for hosting life. However, even JWST's capabilities have limits. For instance, if the planet is too faint or its atmosphere is too dense, the telescope might struggle to detect subtle details. In such cases, scientists will need to turn to other instruments. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, represents a major leap forward in exoplanet research. This telescope, named after NASA's first female chief architect, is designed to conduct large-scale surveys of the cosmos, including the search for planets using the microlensing technique. If the planet was detected through this method, where the gravitational field of a star bends and magnifies the light of a distant object, Roman's advanced sensors could help identify more planets in similar conditions. Its wide field of view and high sensitivity make it ideal for spotting faint, dimly lit worlds that might otherwise go unnoticed. Moreover, Roman's ability to detect subtle changes in starlight could also reveal the planet's orbital characteristics, such as its distance from its star or the presence of a debris disk, which might indicate recent planetary formation. Ground-based observatories will also play a crucial role in this next chapter. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the largest optical telescope ever built, with a primary mirror spanning 39 meters. Once operational, the ELT will have the power to image exoplanets directly, capturing detailed images of their surfaces and atmospheres. This would be a groundbreaking achievement, as direct imaging has only been possible for a handful of planets so far. The ELT's adaptive optics system, which compensates for Earth's atmospheric distortions, will allow scientists to study the planet's light in unprecedented detail. For example, if the planet is a rocky world with an atmosphere, the ELT could detect the faint glow of its surface, revealing clues about its geological activity or potential signs of life. However, even with the ELT's capabilities, challenges remain. The planet's brightness relative to its host star, the distance from Earth, and the presence of background light could all complicate these observations. Beyond these instruments, the scientific community will also turn to theoretical models and simulations to interpret the data. The discovery of this planet may challenge existing theories about planetary formation. For instance, if the planet is found to have an unusual composition, such as an unexpectedly high concentration of heavy elements or a lack of water, it could suggest that it formed in a different region of its star system or was influenced by gravitational interactions with other planets. These findings could force scientists to revise their understanding of how planets form and evolve, potentially leading to new hypotheses about the diversity of planetary systems in the galaxy. In some cases, the planet's characteristics might even hint at the presence of undiscovered celestial bodies, such as a massive unseen companion that influenced its orbit or a dense asteroid belt that shaped its development. Another critical area of focus will be the search for potential habitability. If this planet lies within the habitable zone of its star, where temperatures could allow liquid water to exist on its surface, it would be a prime candidate for further study. However, determining habitability requires more than just location. Scientists will need to investigate the planet's atmosphere, magnetic field, and geological activity. For example, a thick atmosphere could trap heat and create a greenhouse effect, while a strong magnetic field might protect the planet from harmful stellar radiation. These factors, combined with the presence of water, would make the planet a more promising target for the search for extraterrestrial life. To explore these possibilities, future missions like the European Space Agency's Plato, Planetary Transits and Oscillations of Stars, mission could play a vital role. Plato, scheduled for launch in the 2030s, is designed to detect Earth-like planets around Sun-like stars and study their atmospheres. If this newly discovered planet is within Plato's target range, the mission could provide additional data to assess its potential for hosting life. Yet, the journey to confirm and understand this planet is not without its challenges. One of the primary hurdles is the vast distance between Earth and the planet's host star.
Even with the most advanced telescopes, the light from this planet will take years to reach us, and the data collected will be limited by the technology available at the time of observation. Additionally, the planet's faintness compared to its host star could make it difficult to distinguish from background noise, requiring sophisticated data analysis techniques. Scientists may also face the challenge of interpreting the data correctly, as the signals they receive could be influenced by factors such as stellar activity, atmospheric interference, or instrumental errors. These uncertainties mean that the confirmation of this planet's properties will require multiple lines of evidence and cross-verification from different instruments. Moreover, the revolutionary method used to detect this planet could itself be refined or even replaced in the future. The discovery of this hidden world may have been made possible by a technique that was previously considered too risky or impractical, such as gravitational microlensing or direct imaging. However, as technology advances, new methods may emerge that offer even greater precision. For example, the use of space-based interferometry, where multiple telescopes work together to create a virtual telescope with a much larger aperture, could allow scientists to resolve smaller details on distant planets. Similarly, advancements in machine learning and artificial intelligence could help automate the analysis of vast datasets, making it easier to identify subtle patterns that might indicate the presence of new planets. The broader implications of this discovery extend far beyond the immediate study of this single planet. It could inspire new missions and instruments designed to search for planets in even more extreme environments, such as those orbiting red dwarf stars or located in the outer reaches of their systems. It might also prompt a re-evaluation of how we define habitability, as the discovery of planets with unconventional characteristics challenges our assumptions about what conditions are necessary for life. Furthermore, this planet's existence could provide clues about the prevalence of such hidden worlds in the galaxy, suggesting that many more planets may be lurking beyond our current detection capabilities. This, in turn, could influence the priorities of future space missions, shifting focus toward methods that are better suited for uncovering these elusive worlds. In the coming years, the scientific community will continue to refine its tools and techniques, driven by the excitement of this discovery. The collaboration between space agencies, observatories, and research institutions will be essential in ensuring that this planet's secrets are fully unraveled. Whether through the lens of the James Webb Space Telescope, the vast capabilities of the extremely large telescope, or the upcoming missions of Plato and Roman, each step forward will bring us closer to understanding the true nature of this hidden world. As we peer deeper into the cosmos, we are reminded that the universe is full of surprises, and that the quest to uncover them is as thrilling as it is profound. For years, astronomers have searched the cosmos for elusive worlds hidden beyond the reach of traditional detection methods. Now, a groundbreaking discovery has rewritten the rules of planetary hunting. A NASA telescope, employing a revolutionary technique, has finally uncovered a planet that had eluded scientists for decades, proof that even in the vast, dark expanse of space, there are secrets waiting to be revealed. This isn't just about finding a new world, it's about redefining how we peer into the universe's hidden corners. The method used, which leverages subtle gravitational effects and advanced data analysis, has opened a new window into the uncharted, allowing astronomers to spot planets that had previously vanished in the noise of cosmic data. This discovery marks a pivotal moment in exoplanet science, demonstrating that the universe's most elusive mysteries are no longer beyond our grasp. But how did this happen? And what does it mean for our understanding of planetary systems? As we unravel the story of this hidden world, we'll explore the technology that made it possible, the challenges of detecting planets that don't shine their own light, and the broader implications for the search for life beyond Earth. This is a tale of persistence, innovation, and the relentless curiosity that drives humanity to look beyond the stars. If you've ever wondered how we find planets in the dark, or if there are worlds we've yet to imagine, this deep dive will take you there. And if you're hungry for more stories like this about the universe's greatest puzzles, the tools that unlock them, and the scientists who dare to ask, what's out there? Then hit that subscribe button. Because in the endless expanse of space, every discovery is just the beginning of the next question.